So it's 11:30. So let us start this. Santosh, is it okay? Yeah. Okay. So welcome back everyone to this topic of lecture series, that is quantum clocks for fundamental science and metrology. And today is the third lecture. In last 2 days, in last two lectures, I was covering some basic introduction about the clock and particularly the atomic clocks. I was giving the working principle of microwave clocks based on hot atoms, gas cells, and as well as cold atoms, atomic fountains. In last lecture, I was covering different type of optical atomic clocks like neutral atom optical atomic clock and trapped ion-based optical atomic clock. And today, I am going to talk about applications of atomic clocks or precise timing systems, because atomic clocks are the backbone of precise timing systems. So today I will mostly tell you about the technological applications, and next lecture I want to cover how these atomic clocks can be used to explore fundamental science. So I have divided into two different, let's say, subtopics, but both of them are basically applications of accurate atomic clocks. Okay, so let us begin. So today I'm going to mostly cover the technological aspects where the atomic clocks are important and needed, actually a necessity. So before actually I start uh, describing some of the applications, so let me actually impose a question to all of you, and then you can think over it while I'm giving the talks, and at the end I will actually uh, give you more detailed answer to it. So the picture what you see here on the screen, that is actually IUCAA's Giravali Observatory, which is around 50 kilometers away from Pune. It's a very nice place on top of a hill top. And the road what you see here, that reaches to this telescope, which is this Giravali Observatory. And the point B is the top of the telescopes, and point A is just on the road. It's a very nice place to visit. If you have any chance, please visit it. But okay, so the let's say that somebody asked you to measure the height difference between the point A and B. So what would you do? Typically, as a simple, normal, classical way, I would just take this kind of level meters, and then I will stay at point A. I will ask my friend to stay at point B, and then I will make this leveling, and that actually one can measure this distance, horizontal distance between point A and B. Okay. And once you measure this horizontal distance between point A and B, that is D, let's say, then I can also measure using a, let's say, laser pointer the angle. So I would point the laser pointer towards my friend sitting at B, and then make it vertical, and then I would be able to measure the angle theta. One can use a different technique also to measure the angle theta. So basically, if I know this d and theta, then I will be able to measure this height h. Okay, so far so good. It's actually gives a very accurate measurements, quite accurate measurement. So all fine. But now let's say I ask you to measure the height of the Mount Everest. Well, the location is not a very good location to reach there, but still actually using trigonometric techniques in 1988, in which year, it's a long time back, I forgot the year, Radhanath Sikdar used a simple trigonometric technique and measured the height of the Mount Everest very accurate. So what he did, he took some sort of like a torch or something, I don't know exactly what, some pointer, and he was placing himself at a point, he doesn't know at which point it is, and he was able to measure the angle theta of this vertex point of the Mount Everest. And then he moved a certain distance d, and then again measured this angle pointing towards the vertex point of the Mount Everest. So let's say these angles are A and B, and then distance he knew very accurately how much he moved. Let's say that is d, and then just using this trigonometric formula, the derivation is here. I'm not going into that detail. One can actually measure the height h of the Mount Everest by knowing this distance d and this angle a and b, and he did it in 1954. Okay, this is the right year, 1954, using a very simple classical tools, basically rulers and some probably some other pointer. I don't know exactly what it was. And he measured this height of the Mount Everest, 8,848 meter. And just recently, I think last year, there was a like a joint venture by Nepal and China. They used much sophisticated tool and remeasured the height of the Mount Everest, and then they came up to the height. Sorry, this was actually the height that China measured at that time in 1954, and there is a discrepancy of 4 meter. So there is always a like a sort of discrepancy going on, that who is right, Indian measurement was right or Chinese measurement was right at that time. Then recently, last year, Chinese government and Nepal government, they made a joint venture to remeasure Mount Everest. And in today's world, we have much sophisticated tools to measure it. And then the measurement gives the result 8,848.86 meter. So just 0.86 meter different than what Radhanath Sikdar, the young mathematician, measured in 1954. So we should be really proud of that thing, that using just simple tool, he actually measured it extremely accurate. Okay, so far so good. So we know the height of the Mount Everest quite accurately. But now let's say I ask you to measure the small incremental change of the height of the Mount Everest. It's sort of changing its height less than a millimeter every year, because there are two tectonic plates which made the Himalaya. They are still moving close to each other. And as a result of that, how height of these Himalayan mountains are changing, similar to the Mount Everest. And it's very important to know this change, because it can actually model several things, including earthquakes, when the earthquake can come, how these dynamics are changing. So this is an extremely important question, that how these tectonic plates are moving towards each other, and then what we can expect in the future. Yeah, so that is a very important measurement. So now my point is, how can somebody measure the height change with a 1 millimeter accuracy? So here you say this is not in 1 millimeter or sub-millimeter accuracy, but that's what we want to reach. And for that, believe me, atomic clock actually can do it. And I will tell you these things. I will explain you at the end of my today's talk. But let's start with something simple today. So the requirement of precision timing systems, or let's say atomic clocks, because atomic clocks are the backbone of the precision timing systems. They are enormous applications. Basically, you can name almost anything which you are using in your daily life, or in strategic sectors, in defense, in space research, anything. All of them required very precise timing systems to actually work. Even let's say you are drawing some money from the ATM bank. If you look into the slip, it gives a timestamp at what time you are drawing that money. So it's called digital archiving. Yeah, for any transactions you are doing, any if a form you are filling up for anything, it always gives a digital archiving, and it's very important for the security purpose and for several other purposes. So it requires a precision timing system, and it comes from the atomic clocks, actually, from GPS clocks, or some sort of that kind of very accurate clocks. Other than that, more sophisticated, like let's say targeting, very accurate targeting, then cyber security, then navigation systems, satellite based navigation systems, which nowadays almost all of us use in the Google Maps, or some sort of this kind of satellite based navigation systems, accurate positioning of the satellites into their orbits, high speed communication, like any communication, basically 4G, 5G, or maybe forthcoming 6G, any communication required actually very accurate timing systems. So I won't be able to describe all these. I mean, there are enormous applications, so it's not possible to describe all of them. But let me just pick. I have picked few of those things which almost all of us commonly use in our daily life. And one such example is the navigation. Like whenever nowadays we go somewhere, either walking or driving a car or in a scooty or scooter, if we don't know the location, then we just simply start on our mobile phone the Google Map, or something else, probably in like in a Mac system, Apple systems, but some sort of just satellite-based navigation systems, and then just type wherever you want to go. It automatically finds our locations at that time, and then it can tell you how, in which directions and which paths you have to follow to reach to your desired location. But let us understand how actually it works. So let's say you are somewhere. I picked up somewhere in like not in Pune, but somewhere in Delhi. You are somewhere, and you wanted to know your location. And then what you do, you just start this map. And then what happens if your mobile device has some receiver, GPS receiver, and also transmitter. So this receiver starts to receive signal from the nearby transmitters. You probably have seen these big these antennas on top of the buildings, or sometimes on top of something something which is higher than normal heights. The small telephone, like mobile transmitters from different service providers, let's say like Airtel or Vodafone, and etc. etc. You have this, you can see these antennas while you are walking on the road and etc. So these are basically the transmitters and receivers. So they transmit these signals all the time, and your mobile device actually receives these transmitted signals. These transmitted signals are sort of in wave packets, and when it starts to come out from those antennas, it gets a timestamp there. Like at, let's say, time t 0, it starts from the transmitter, and when it reaches to your mobile devices or the receiver, then it also gives the timestamp. Like, let's say at time t prime, it reaches to your mobile devices. Then the data packet has the information when it starts from the transmitter and when it reaches to the receiver, and from that it calculates the time it travels. Let's say that is t1, so that is t0 minus t prime. So this is the time it took to travel from the transmitter to the receiver, and it is traveling at the speed of the light. So if you can multiply, if you multiply speed of the light with this time difference, let's say that is t1, then you will get, basically, your receiver, that is your mobile device, can calculate at what distance this transmitter is, that is distance d1. But you don't know exactly in which location the transmitter is, because it can be in on the circumference of a circle which has a radius of d1. So you can be anywhere in that circumference. So that means your mobile device or your location, basically, you don't know exactly, but you know that I am at a distance d1 from that transmitter. So only one transmitter won't help you to find your location. So you need more than one transmitter. In case you have two transmitters, so basically, let's say your mobile device is receiving signals from two transmitters at the same time, then you will get two point of interactions between two circles. So same thing will happen with this transmitter also, and then you can also, one can draw another circle, and then these two circles will have two intersecting points. It is this yellow dots. Yeah, so then your mobile can say, okay, either I am here or I am in this location, but you still you don't know exactly where you are. You can be anywhere between these two locations. So you need at least another transmitter, that is a third transmitter. Then you basically do the same thing like this, draw the circle. I mean, you means your mobile device does it automatically with the proper algorithms, and then these three circles can intersect only in a single point, and then your mobile device can actually find, okay, I am exactly at this point. Okay, that's what's the basic principle how this all this satellite based navigation system works. Okay, but actually this is a two-dimensional description of the entire thing. Actually the earth is three-dimensional, so everything is three-dimensional. So you need at least four transmitters or more than that. So just to give you an example, like sometimes you will see that you won't get enough signal on your mobile devices, and then we say, oh, tower available nahi hai, etc., etc. But actually, what it means, the mobile device is unable to connect four transmitters at the same time. If it is not able to connect to four transmitters at the same time, it doesn't work. That's what it basically what we mean, like a tower nahi mil raha hai, etc., etc. So it may be connecting to 3 or 2, but not 4 at the same time. And then we get very small signals and all these kind of these markers and etc. Okay, but then what do we need if I have to find out the location of a particular devices in this point? So basically, all these transmitters as well as the receiver has a clock, internal clock. Yeah, and these clocks have to be stable enough so that it's not deviating away from its timekeeping, and also have to be synchronized. Yeah, otherwise it won't work, because the data packet which is carrying a time information, also this clock and that clock have to be synchronized. Else, I mean, if they are not synchronized, then the time difference will be miscalculated. And then this distance, then D1, D2, D3 will be completely miscalculated. So one important thing is having a very accurate stable clock into all these devices, including transmitters and receivers, and all these clocks have to be synchronized. How well they have to be synchronized? Let's say the synchronization is within 1 second accuracy. And in 1 second, light travels 3 into 10 to the power 8 meter per second. So if the accuracy of the synchronization is 1 second, your location will have an inaccuracy of 3 into 10 to the power 8 meter. So that means you could be here or you could be in the moon. You don't know. So the inaccuracy of your position is something like that. 3 into 10 to the power 8 meter, which doesn't work. So that means you have to have a clock which is extremely accurate on the order of nanosecond accuracy, 10 to the power minus 9. So for example, if you have a want to receive 1 meter accuracy, then the clocks have to be 3 nanoseconds. The synchronization inaccuracy can be maximum 3 nanoseconds. You can calculate it, very simple thing. So basically 3 nanosecond inaccuracy will give you 1 meter accuracy of your position, which is good enough for most of our purpose. Yeah, right. And typically the GPS clocks have on the order of tens of nanoseconds accuracy. So that means you can see, you can find your location within about tens of meter inaccuracy, and that's what typically we see when we start Google Maps or something like that. Yeah, it could be 10, it could be 20, but on that order. Yeah. So basically what I wanted to point out here, two things. One is important, very important aspect to this, to get this GPS based communication to actually work. You need very stable clocks, and also they have to be very well synchronized. And as the good, as the synchronization is better and better, you can actually find out your locations in a much accurate way, and etc. Well, let me give you another example which might tell you, which might actually tell you a little bit more about like how important is this time synchronization. I mean, hopefully that you have traveled through flight. If not, just believe me that whenever a flight takes off or it's landing, during these two times, it never works in an autopilot mode. It's always a pilot is actually handling the flight by himself, the manual mode, still now. But whenever it's actually flying on sky, many times it's in autopilot mode. So basically, pilot have to just monitor things are working and etc. But flight is actually in the autopilot mode. Everything is automatized to remove the human errors and etc. Now the question is why this autopilot is not there when it is landing or when it is taking off, because the typical diameter, sorry, width of a runway is, let's say, around 20, 25, sometimes 30 meters and etc. And typical GPS signals accuracy is on the order of 10 meter. So that means, just roughly speaking, between friends, you cannot, the if it is in autopilot mode, then it won't be able to find the location or the path of the aeroplane with, let's say, plus minus 10 meter accuracy. So then it could be on the runway or it could be out of the runway if it is in autopilot mode. So it doesn't work yet. So that's why actually during these two times, pilot have to control the plane by himself and actually look by his own skies or light guides and etc., and have to take it for the landing or takeoff. If we can improve this scenario to from, let's say, tens of nanoseconds to a few hundreds of picoseconds accuracy in the future, then everything can be autopilot mode. And let me tell you that most of the mishap happens for flight, it's during the takeoff or during the landing. because it's a mostly human errors. Yeah, so that can be largely avoided if we can actually make everything autopilot, and that requires more accurate timing systems. So that's a demand, like why we have to have much more accurate timing systems. This is just one example. Okay, so now I have introduced you about the time synchronization, and already I introduced you about the stable clock. But now we have to remember, for most of the practical purpose, uh, we have to maintain the local times. So you know that the entire world is divided into several time zones, depending on basically when sun rises and sun sets at that particular locations, and there is a different 24 time zones, and each time zones are separated by 1 hour, right? You can see the picture basically somewhere. But now how, and so how we can maintain the time, the accurate time of these individual time zones internationally. That means the time zone in India has to be really matched or synchronized to the time zones in US, and similarly all other countries, and vice versa. So how one can do that? If there is an asynchronization of these time zones, then the flight communication and everything won't work properly, and it has to be synchronized really very accurately. And I gave you an example. So for that, what happens, uh, in 1857, in the meter convention, there are several international like several countries came together and thought of this problem, and they established BIPM. So BIPM is an international agency which was established through meter convention in 1857, and the mandate of the BIPM is to maintain SI units. SI is international standard units for all fundamental and derived quantities, like let's say time, mole, then temperature and mass. There are total 7 fundamental ones, and then several derived ones. So maintain these things, these units of these quantities in an international level. That's why it's called SI units. For example, for time, the SI unit is second. For length, it's meter. For temperature, it's Kelvin. And for quantity of something, it's mole, and so on, so on. So these things has to be really maintained at the international level. So let us focus on second, or time, for our discussions today. And it has an additional role, that is this last one, that is international reference time scale, which is UTC. It's universal coordinated time. So basically what it does, there are several atomic clocks around the world, around let's say 400 or 450. So all of them, they give their input to the BIPM, and then BIPM actually statistically, it's not just simple statistically, it's weighted average. They take an average and maintain the SI second extremely accurate. I think it's within zero point 0.3 nanoseconds or something like that, if I remember the number correct. It's extreme, or maybe even more nowadays. So it's extremely accurately they maintain this SI second, and then disseminates it to the all over the world, to all the countries. And India is also one of the member of this BIPM, this international agency. India also have a stake of that thing, that BIPM, and India also gives its time from NPL India in Delhi, and contributes to maintain that international time scale. So that's also we should be proud of here. So for to understand little bit more, we have to understand few fundamental, let's say, definitions and etc. One is universal time. The nomenclature is UT1. So universal time is a non-uniform solar time that is based on Earth's rotation. So basically, what it means, it's solar time, like when the sun rises and when the sun sets, and it depends on at what frequency Earth rotates. Now, the rotation of the Earth is also not a constant thing; it changes very tiny bit over time every year. So basically, one have to measure how this rotation of Earth is changing, even if it is so minute. How it happens? I mean, how we do it? basically we take the help of these radio antennas which are used for astronomy. So let's say, so it's called VLBI, very large baseline array. So let's say one radio antenna in India and the other one is in Arizona. Just to take an example, that's a very large separation between these two radio antennas. They detect radio frequency signals coming from quasars. Quasars are at a very, very long distance, very, very far away from Earth. So they produces radio frequency signals, and these radio frequency signals on Earth you can consider as a plane wave. So these plane waves are appearing into the to these two different radio antennas, but at a different time, because these two radio antennas are at two different locations. So let's say there is a time difference of appearance of these radio frequencies from the quasar, and this time difference is, let's say, CT, and you know exactly the location of these radio antennas because they are fixed on two different points of the earth, and that can tell you what is this blue line, and that if the rotation of the earth changes, then this CT will change. Yeah, because they will appear at a slightly different time on these two radio antennas. So for that, you have to have synchronization, time synchronization between these two radio antennas very, very well. Then only you can measure what is this tiny bit of changes. Okay, so that was an application of the atomic clock or very accurate clock systems. But however, here the point I wanted to make, this is the way how the slightly bit change of the rotation of the earth is actually measured using the radio antennas or VLBIs. And the time scale, the solar time scale is determined by that very accurately. It's called universal. Okay, but now today's world, we actually maintain the international reference time using atomic clock. So the previous one was solar time, which we measured through VLBI. But now actually the time scale is maintained by atomic time. Atomic time has nothing to do with the solar time. Two things are completely independent. One is just an atomic clock, which is sitting on Earth or somewhere else, and one is just rotation of Earth. Okay, now how the atomic clock is maintained, that is this international atomic time. I already explained that. So there are several of these atomic clocks, as you see here the picture, and they give input to the BIPM, and then BIPM basically statistically weighted average. They do it with their complex algorithms, and they maintain this international standard of time very, very accurately. Okay, now these two things are very important ones, but two things are independent ones. So now we have to make a connection between UT1 and TAI. One is atomic time scale, another one is solar time scale, and that is actually after this bridging the gap between UT1 and TI. It's called UTC, Universal Coordinated Time. So basically, what it is, one has to look into change of the earth rotation by this UT1 techniques and etc., and then have to make the corrections accordingly into this TI, atomic time, and that's called leap second corrections. Basically, without going into very deep into detail how it happens and etc., it's called leap second correction. So when this total time change, or time change means basically what I mean that one this topical year, one topical year changed by 0.9 second, it's plus 0.9 seconds or minus 0.9 second, then the atomic time, the 1 second is added to the atomic time or subtracted from the atomic time. That's called leap second correction, and that's how the UTC, Universal Coordinated Time, is created from this atomic time. So basically nowadays we actually do the timekeeping in international level from the atomic clock, but that is synchronized to the solar time using this entire complex techniques. Okay, so now we know what is UTC, Universal Coordinated Time, how it is maintained by the atomic clocks, and how it is synchronized to the solar time. Now the actually instrument in the laboratory, how it does. So these are the pictures which I have taken from NPL. This is the setup from NPL. So NPL in Delhi, in NPL India basically. So these are constellation of the atomic clocks. There are several of them, and they basically do the timekeeping very locally. They realize UTC, Universal Coordinated Time, at a great accuracy, and then that is being disseminated to the BIPM. That's given to the BIPM using satellite techniques. So it's called CVGNSS, Common View Global Navigation Satellite Systems, or two-way time transfer, TWSTFT. So there are two different time transfer techniques. Also, there is another one called fiber coupled time transfer techniques, which we don't have in India right now, but that's a more accurate one. So using different dissemination techniques, basically, let's say this realization of the UTC is being disseminated to the BIPM, and similarly, BIPM gets input from all other 400 or 450 clocks worldwide, and then they statistically average it, and that is being even given back to all the countries. So India also receives that standard time through the GPS synchronizations again. So it's a two-way thing, and then this local time scale is being corrected. So you can basically locally, one can see how much he is deviated from the UTC and then make the corrections accordingly. That's how it is done. And that's how this standard of the time for any country is being maintained, including in our country. That is called Indian Standard Time and maintained by NPL. And then that is being disseminated to the common man, to the pan India in many different ways. And that ways basically, if different techniques have different sort of level of accuracies, and for example, ISRO also receives this time Indian Standard Time very accurately from NPL, but they uses a much complex techniques than a common man required. So typically for all the common mans and etc., the it's being disseminated through networks, through internets nowadays, or through telephones also. Okay, so I'm not going into detail of those techniques and etc., but I just wanted to give you an impression how a country maintains its own time at par to the international standard. Okay, and instead of GPS, India is going to have, or actually already having, its own satellite navigation satellite systems. It's called IRNSS, Indian Regional Navigation Satellite Systems, and from our space research colleagues, ISRO, and they have 7 satellites in space, as you see here, and they are able to maintain they are basically not able to maintain. Time is maintained by NTL, but they are able to disseminate this Indian standard time with 7-second inaccuracy. Somehow it is written. So it's 7-second inaccuracy, and that corresponds to 20 meter of position inaccuracy. So 1 second corresponds to 3 meter. So 7-second corresponds to roughly, let's say, 20 meter. So they claim that they will be able to measure they will be able to measure location of any point within 20-meter accuracy, which is practically good enough for many purposes. Okay, and that's very useful. So that's also, we are basically going to be independent of the GPS based time location, which is coming from US, and we will have our own IRNSS systems developed in the country, indigenized. Okay, so now once I talked about the time synchronization, time keeping, and etc., using cesium clocks or microwave clocks, so that's the sort of mapping of the different cesium clocks available worldwide, and also now there are actually several network experiments coming. So I'm now going from typical technological applications to more scientific parts, and astronomy is one of the very good example where very accurate atomic clocks has lot of applications. You know that VLBI, there are several radio antennas distributed worldwide, and they are all networked. They are connected. They are basically looking into the same object at the same time, and then they basically enhancing their scope of the measurement. And for that, all these VLBI antennas have to be very accurately time synchronized. I will come to that in a minute, but uh, without the actual time synchronization, this VLBI won't work. And the backbone of that is again atomic clock. Similarly, there are several gravitational wave detectors. I mean, we know that there are 2 LIGO detectors in US, then Kagra in Japan, then Vargo in France, and India is also going to have its own LIGO. So all these gravitational wave detectors also have to be very accurate time synchronized. I will discuss that thing also in detail. The next generation event horizon telescopes, there are like several of them will be connected together. So for all these applications, for radio astronomy or optical astronomy or gravitational wave astronomy, the synchronization among the detectors plays a very important role to actually determining the scientific answers. If the synchronization is not available, then the detectors won't work, the networking of the detectors won't work properly. Then there are other experiments other than astronomy. For example, the very accurate magnetometers, which maps the Earth magnetic field very, very accurately. And then there are science interest why this needs to be done. And you see that there are several of these very accurate magnetometers located in different parts of the world. They also have to be time synchronous. So for any network experiment, basically without time synchronization is not possible. And fundamentally the reason is all these distributed detectors need to know exactly at what time they are receiving this signal, and they have to make then a correlation between the signals, like the signal that one antenna or one device that was detecting is same as the signal which other device in a different continent was looking, or it was something different. For that, one have to have the time synchronization. Another example is, let's say, this atom interferometry, which measures g, small g, which measures basically the Earth's gravity very, very accurately. And this is a networked experiment within UK. They again like the same time synchronization. And obviously the optical atomic clocks, which I will discuss in more detail in my next lecture, they have to be time synchronized very, very accurately for fundamental science investigations. So takeaway message is basically the time synchronization among is very important for various experiments, and atomic clocks plays the is the backbone for this all these things. So now coming back to the radio astronomy as an example. So here I have taken the example from our GMRT, just nearest neighbor. So there are like total 30 antennas which are distributed over 25 square kilometer area, and each of the antenna have a diameter of 45 meter. All these antennas are basically looking into the sky and looking into the same signal. They are detecting the same signal. Why we need the 30 antennas? Because it's increasing the basically, how do I call it, like scope of view, let's say. If you have only one antenna, you are looking you are focusing only to a particular part of the sky. But if you increase number of antenna, your this like the how much you are looking into the sky, it increases. There probably is a technical word, like I don't know exactly what it is, like how much like how much portion of the sky you are looking, that increases if you increase the number of antennas. But then the point is all these antennas have to be synchronized. Basically, all the antennas which are receiving some sort of signal, which is very tiny signals and etc. etc. Now, how do you know that signal from one particular antenna and signal from other particular antenna, they are uh, uh, they are at any instant of time, they are looking into the same things or not? So that means these antennas have to be time synchronized, and not only time synchronized, also phase synchronized. Yeah, then only you can make a very good correlation among the different signals received by different antennas, and then you sum up in a complex way and then enhance your signal. Otherwise, it will be just a noisy, because your signal from one antenna and other antenna, they will not be properly synchronized or something like that. But if you synchronize, then it will be like that. You just add up. You can add up properly. So time synchronization is very important role for like any radio telescopes. As an example, I told you about the GMRT, and I let me tell you, this was a news article in 2018 by GMRT. So they are saying, this is an Indian Express. So they are saying accurate keeping of time and frequency are two of the most important needs of any observatory, for which the heart of the GMRT is also being upgraded to an hydrogen measure. So they brought an hydrogen measure, which is an atomic clock, in 2018 or so, and they upgraded their GMRT in their capability of the GMRT using this atomic clock technique. a setup that helps to maintain a better standard in time and frequency in their setups. So that's what was a news article from GMRT, and that is actually what they have done for enhancement of GMRT's capability. Now let me go into the another example, that is LIGO. So let's say a gravitational wave is coming from some portions of the sky and etc., and it basically just passes through the Earth. Now there are several LIGO detectors, as I have pointed some of them, including like LIGO detectors as well as other gravitational wave detectors like Kagra and Virgo. So they are not at the same time on all these detectors. So there is a time delay, yeah, because of the location of these detectors. Now, if you know the location of the detectors very accurately, and if they are time synchronized properly, you can actually again adding up the signal and you can enhance your capability. So for example, the first gravitational wave which was detected in 2015 or reported in 2015, no, actually detected in 2015 and reported in 2016. So in Hanford and Livingston, two different LIGOs. So these are the two different signals. So the blue one is from Livingston and the red one is from Hanford. So this is the signal from gravitational wave, and the signals in these two observatories have a 6.9 millisecond time difference. So signal that arrived in one of the detectors, uh, uh, and then it was 6.9 millisecond delay to reach to the other detector. If you know this time difference very accurately, that will help you to point out where this gravitational wave was actually created or happened very accurately. So 6.9 millisecond was their accuracy, but it can be enhanced further with improvement of the optical atomic clock instead of just microwave atomic clocks, and then these locations can be also calculated more accurately. So it's very important to have the time synchronization among all these detectors. It could be gravitational wave detectors, it could be radio antennas, or it could be any other experiment. So this I just took these two examples because these are more astronomy related and etc. Okay, now let's come back to let's move further and let's come to more accurate clock, that is optical atomic clock. So far everything is done actually using the microwave clocks, but there is a need that it has to be much more accurate than what we are using right now. And I gave you an example like this autopilot thing, which is an easy example to understand, but there are many other complex examples. Let us not go into that detail, but clearly there is a need of going to much better time synchronization, even for technological reasons, without even going to the fundamental science and etc. So optical, this slide actually I already showed you probably last time. So optical atomic clock is important for various reasons. One is maintaining the standard of the time much more accurately. So right now we are maintaining with like let's say 0.3 nanoseconds and so on, but it could be sub picoseconds and even much more, much better. And that will basically help different technologies, as I have written at the end, like time stamping and time synchronization throughout the world. And why they are important? Because of the strategic reasons, for the navigation, for the communication, cyber security, anything, transportation, many things. And the optical atomic clock helps to explore fundamental science, which is the topic I will discuss into the next day. So let me just take one example where much accurate time synchronization is needed. We have heard of the communication, just classical communication, GPS based communication. But now the next thing is quantum communication. When I say next thing, it's quantum communication is already established, but it's not yet used, let's say, commercially. It's still in the experimenting, uh, uh, like it's still not available for the commercial uses or anything, any other thing. Sometimes in some of the advanced countries, people are using it for the strategic reasons, but still it's an how do I call it, like it's an emerging technology but not an readily available technology at this moment. Okay, so how the quantum communication works? Basically the quantum informations are encoded into photons, and these photons are disseminated from one location to the other location. So let's say this is one location on Earth and this is the other location on Earth. How can you disseminate the photons from two different locations which are thousands and thousands kilometers away? So one thing is you just shoot a high power laser where the photons are encoded into quantum bits, and then you are shooting it into some satellites and etc. And then satellite will have some sort of reflector, and then it will reflect back to the other location. That's what people use. The other thing could be there are optical fibers connecting between these two locations. There are optical fibers already available for classical optical communication, normal optical communication, and but you have to do a little bit more to use them for the quantum communication. But the point is, one can decipher as well. So this is an example where the quantum communication, the satellite-based quantum communications were first reported or tested, and this is by Japan. So the setup is following. So they produce these quantum photons where the quantum informations are encoded into some experiment, and then they send it through the satellite. Then the satellite reflects it back, and then there are some telescopes which receives these photons and then comes back to the lab for decoding that quantum information. So that's basically the sort of setup in simple words. It's not that simple, it's extremely complex, but in simple words, that's how it happens. And there I am just taking the paragraph from their paper, from this Nature paper. So this is the signal that arrives at a 1 meter telescope, that is this one, it gets attenuated. There are many dust particles and etc. It gets scattered. So finally, on the other side of the receiver side, the number of photons appearing is very small per second. So the signal to noise is extremely weak. So that's what they say. NICT developed the technology to perform the time synchronization and polarization reference frame matching between the satellites and the ground station directly from the QKD. QKD is quantum key distribution signals, as well as the quantum receivers capable of detecting such a weak signal with low noise. So basically what they say is time synchronization, they have developed this very accurate time synchronization technique, and that because of that they are able to detect that weak signal. So there is another paragraph in the same paper. In order to realize quantum communication and quantum cryptography with such a weak signal, a key step is to accurately timestamp the signals so that they are clearly recognized in the quantum receiver. Therefore, it is necessary to accurately synchronize the signals between two locations, that is Socrates and OGS ground station, to detect the transmitted bits without error. So basically the point is, if somebody have to do the quantum communication, which could be either satellite based techniques or optical fiber based techniques, between these two locations, time synchronization and time stamping on the data is extremely important. It's much more, one have to do it much more accurately than a classical communication. And the only way to generate that sort of accuracy, let me not go into these details, so let me skip. So now I am coming back to answer the question that I actually asked in the beginning, like how to measure the change of millimeter scale height of an earth, of the Mount Everest. So scientifically, this is called actually geodesy. Geodesy is measuring the Earth's directions and shapes and gravitational field. So basically mapping. All these parameters changes time to time. Yeah. So mapping of these parameters of Earth is called geodesy, and accurately that can be done using clocks. So the picture what you see basically is a surface profile of a particular tiny location, let's say very tiny one here, and then the green one is just the surface area. So somewhere it is a hill, somewhere it is a very deep under the ocean. The the yellow is average radius of Earth. So the spheroid, if you just consider Earth as a sphere, then this is just the surface of the spheroid. The blue one is the average actual sea level. Blue one is the actual sea level at any location. So for example, this here in this part, the Earth's surface is at much lower than the sea level. So that means there is a sea, and here is some ocean, and etc. etc. and this magenta color is actually geopotential, equipotential surface due to the Earth's gravity. So surface, the gravity, Newton, sorry, the Earth gravitational potential is not same everywhere. It changes because of the availability of the mass. Somewhere it is a hill, so the gravitational potential will be a little bit higher. Somewhere it is an ocean, so there it should be a little bit bottom. So the gravitational potential is not like a spheroid. So this also has some sort of dynamics, and that's what you see here in the magenta. And it's very important to measure this magenta one, or let's say the geode of Earth's gravitational potential very accurately and keep track of that. That will tell you if there is something a change on or a mass distribution on Earth's surface. This mass distribution could be volcanic eruption, or could be like breaking of some iceberg and etc., where actually the lot of mass gets distributed, and that changes, and that is very much related to the atmospheric changes, global warming, and etc., all these sort of things. So it's very important to map these things, geopotentials, very, very accurate. And that can be only done by optical atomic clock. So let's see how it does. So the change of geopotential delta U by change due to the change of height from the Earth's surface can be written like that. This is a very simple formula we know, like Newtonian potential on any on Earth's surface is G, capital G times ME by RE, where capital G is gravitational constant, ME is the mass of Earth, and RE is the average radius of Earth. And if you go to a higher height, then it changes like that. So that means delta U, change of the Newtonian potential, can be written as subtracting these two from each other. And if you do a little bit math, then delta U becomes G, capital G times ME divided by RE square times H. And if you put these numbers of G, ME, and RE, then basically it can be simply written as 0.1 times H, where H is in centimeter unit. Okay, and then we know the fractional accuracy that I was introduced in my last lecture. Delta fractional accuracy of clock is delta F by F0, is also changes as you go above the Earth surface, gravitational redshift, and that is basically dependent on this delta U, change of the gravitational field. So this change is how they are connected to each other. So delta F by F0 is equals to delta U divided by C square, where if I use the delta U from these relations, then I can rewrite delta F by F0 due to change of height is 0.1 by C square times H. H is in centimeter unit. And then if I put all this formula, all these numbers, then it is sort of 10 to the power minus 18 times H. So if I have a clock which is accurate, which has a fractional accuracy delta F by F0, 10 to the power minus 18 order, that means I can measure the height difference of 1 centimeter. What does that mean? If I keep a two atomic clocks, which is, one is here at the bottom and other one is above, which are separated by only 1 centimeter, if the clocks have an accuracy of 10 to the power minus 18, then actually the tick rate of these two clocks will be different. And by measuring these tick rates very accurately, I can actually measure whether this 1 centimeter difference. So, but now the clocks have reached to an accuracy of 10 to the power minus 21 level. Sorry, let me just go back to here. So, clocks in February 2022, the reported most accurate clock has an accuracy of 7.6 times 10 to the power minus 21. So that means using these two clocks, one can measure the height difference at an accuracy level of sub-millimeter. Okay, so the two clocks which are at a two different height of just less than even a 1 millimeter separation, the tick rates will be different, and that can be measured very accurately. So if you can miniaturize these clocks in a small box which can be transported on top of the mountain, on top of the Everest, then basically if you have place two clocks, one is on top of the mountain, let's say this one on top of the Everest and one on the bottom of the Everest, then these two clocks will be able to measure 1 millimeter or sub-millimeter change over 1 year or so on. And that's not very far in the future. You can see these optical clocks, which are very accurate. They have been miniaturized into small boxes. So this is one of the picture which is not yet commercially available, but we expect to have them in 2-3 years from now. So actually these things can be placed in different locations, and this can monitor small changes of height, let's say less than 1 millimeter. Similarly, it has several other applications, as I told you today in during my talk. Okay, so let me conclude my today's lecture. So I told you several applications about of the microwave clocks, which are state of the art accuracies 10 to the power minus 16 level, like communication, standard communications, navigations, etc., etc. And today we have reached to an optical clock accuracy 10 to the power minus 21 level, and the application of such a like extremely high accurate clocks we'll be learning during my last and next lecture, that is exploring fundamental science. So I would stop here, then I am ready to take questions. So one question I can already see here, that is Tanmoy Pati is asking, for large array radio telescopes, what we do use for synchronizing UTC. One of the most common one are the GPS. So for example, in your computer, if you have a computer or a laptop, you can synchronize your computer with respect to an UTC. You can go to the settings of the time and etc., and you can connect it to the actual UTC or the Indian Standard Time, which is derived from the UTC by NTL India, and there are possibilities to set these things up. Time.ntlindia.org, if I remember correctly. So you can synchronize it with respect to this domain. So yeah, so basically what I wanted to mean that these large telescopes, they receive this UTC information through GPS receivers, and then they synchronize it. A much better way of doing that would be actually optical fiber connections, and that is the next level. Are there any further questions? I don't see any hands up. Yeah, so there is one from Subhadeep Datta. Can you unmute?
Hello, sir. Am I
Yeah,
audible?
yeah.
Sir, my question is when we synchronizing a satellite clock with a clock at rest on the surface of a rotating Earth, do we also need to apply the relativistic effects, or
Yeah,
how can?
absolutely, absolutely. So these are actually already corrected. So the GPS receivers have all these algorithms and they correct it. So that's your question is actually very correct. So when you are using a GPS receiver and when you want to, if you want to do very accurate time synchronization, you have to actually give the location of the, you have to determine location of these GPS receivers very accurately. So there is a different technique, and then you have to give these informations to the GPS receiver, and then it has its own algorithm to make all these kind of corrections, and then it will generate the actual timing information. Okay, so I hope I am able to answer you, Subhodip. So then there is another question by Tanmay Pati. Can you please tell again between two time zones when there are abrupt changes in time, how autopilot works? Well, there is no abrupt changes. The changes between two time zones are known, and that information the receivers always get. So the autopilot can basically work using their proper algorithms. So there is no time like there is nothing abrupt here. Everything is very accurately known. Everything is very accurately defined. So I don't know what exactly you mean by abrupt. So there is nothing abrupt basically. So there is one question by Chetan Agarwal. Chetan, can you unmute?
Am I audible, sir?
Yeah.
Yes, sir. Sir, so as you told that we put a gravitational wave detector
Sorry,
on Earth.
your voice is not audible properly. Can you say a little bit slower?
Yes, sir. Sir, so you said that we established gravitational wave detector at Earth, na?
Huh?
So is it possible to put the detector on space? Means will we be getting a correct result there?
Okay. So your question is basically whether there is any proposal to place the gravitational wave detectors on space. If I understand the question correct, is it?
Right.
Yeah. So
Yeah,
okay.
exactly.
So correctly speaking, I am not a gravitational wave physicist. So it's probably not right for me to answer that question. But since you asked, yes, there is a proposal in the future. It's called I am forgetting the name, Einstein's telescopes or something like that, or maybe something else name. I'm forgetting the exact name. So there is a proposal to place gravitational wave on the space as well. For yeah, but it's in the far future. I think 2040 or 44, something like that. Okay. Any other questions? I don't see anything. So thank you then. So tomorrow I have the last lecture. Thank you for listening. Bye.